Now we're going to continue our analysis for the third joint in our truss. Okay, so we've gone from the first to our left, then to our second from the left. Now we're on to our third joint just here. And we're going to continue our analysis of the method of joints to work out the forces in these two members which are connected to this joint. So just repeating what we've learned before, these members push or pull against that joint doesn't move, so therefore all the forces must be in balance. Now, we have some known forces. We know that the force down the bottom here is in tension, so it must be pulling that joint away at 560 newtons. We know that 871 newton force is also in tension, pulling it away. Now that 871 newton force is so far is the only one with a vertical component. The other one with the vertical component, it must be pushing down with that same amount. Okay, so it must be pushing down, so therefore it must be in compression. The joints are pushing back on that. All those forces, if you look, are definitely pushing the joint to the left. So we know that that final force there must be pushing towards the right. If it's pushing towards the right, pulling it towards the right, that means the joint's trying to pull back on it, which means that member must be in tension, and similar argument for the top one, that must be in compression. So if we take these away and have a bit of a closer look at them, we can write down some information that we know. Now, a similar argument from before, we don't have to keep going through too much maths. We know that that's 871 newtons, we know that's 50 degrees, we know that's 50 degrees. The vertical component of that 871 has got to be balanced by the vertical component of this member in compression. Because of the same angle, to have the same values, those two forces must be the same. So let's write that down right from the word go, that C has got to equal 871 newtons in compression. That is pushing that joint downwards. Continuing on, we have 560 newtons here. We have 871 newtons, but the horizontal component pushing it that way. We have the horizontal component of this one also pushing it that way. This is 871, that's 50 degrees, so we have 871 times cos of 50 pushing that way. That's also 50 degrees, so we have 871 cos 50 pushing it that way. That force plus the horizontal component of this force plus the horizontal component of this force all must be balanced by that one. So let's make it really nice and quick and easy. We know that the force T in this case, which is a member under tension, is going to equal that 560 newton force plus 871 times cos 50. And C is also 871 cos of 50, so let's just write 871 cos of 50. Let's just make sure that's understood. C is 871, so the horizontal component of C is 871 cos of 50. The horizontal component of that force member is also 871 cos of 50. From the analysis in the previous joint, we knew that two 871 cos 50s together for that top member was rounded up to 1120 newtons. So you don't have to work all that again, but obviously you can. 1120 plus 560 is so 1680 newtons in tension. Okay, so we see that the forces are getting bigger there. So already we're looking at a bit of a pattern. These 871 compression, tension, compression. Yeah, I guess we might be thinking if they can be in tension at 871. And we just worked out these two. Okay.